Welcome to this Achronix training video. Today we will introduce the machine learning processor, which is a powerful maths-based element available in the Achronix 7nm range of devices. The machine learning processor, or MLP72, is composed of an array of multipliers, adders and accumulators, allowing for powerful and densely packed maths operations. The MLP is tightly coupled with block memory, BRAM, and logic RAM, LRAM, also referred to as a register file. This allows for reuse of input coefficients or partial results. The MLP contains 16 integer and 2 floating point dedicated multipliers. The MLP output stages have a flexible array of adders and accumulators, so that the output of multipliers can be assembled and aggregated to perform a variety of functions. As can be seen, the MLP contains a high number of parallel multipliers. This allows for very large numbers of simultaneous multiplications, up to 32 in a single clock cycle. Firstly, before processing any data, we need to get the data input to the MLP. The input to the MLP supports a variety of different sources. The 72-bit input bus, the 72-bit shared input to the coupled BRAM, the 144-bit output of the BRAM, the 144-bit output of the coupled LRAM, and finally cascaded inputs from the MLP in the same column below. All these sources can be used independently or combined to derive the input buses to the multipliers. To drive 16 8-bit multipliers, you need 256 bits, which is why a combination of different sources is used to select the input data. In this diagram, you will also see a flip-flop symbol with dotted lines. This represents an optional delay stage within the MLP. There are several of these delay stages throughout the pipeline. They are used to either enable time enclosure at the target frequency, or to allow the MLP to match the latency of the surrounding circuits. For lower frequency designs, then many of these delay stages can be left out of circuit and so reduce overall latency throughout the MLP. For higher frequency designs, approaching the fabric speed of 750 MHz, then some of these delay stages will need to be enabled. Once the relevant input source is selected, the format of the input values must be specified. Currently, the MLP supports more than 20 different formats, ranging from signed 3-bit integers through to 24-bit floating point values. The range includes signed, unsigned, signed magnitude, block floating point, and floating point types. Let's look in greater detail at the integer multiplier functions available in the MLP72. Focusing on the multipliers, as described, there are 16 8-bit times 8-bit multipliers. These can then be combined or subdivided to support from either 4 16-bit multipliers up to 32 4-bit multipliers. The subdivision or combining of the multipliers is done automatically by the MLP, based on the input number format that the user specifies. The output of each multiplier is summed with its 4 nearest neighbours. In the special case of 16-bit values, the 4 multipliers in a group are automatically combined to create one 16-bit multiplier. Subsequently, each of these quad multiplier stages can be summed together. In total, there are 3 buses that are output from the integer multiplier stage: the sum of the lower 8 multipliers, the sum of the upper 8 multipliers, and finally the sum of all the multipliers. The integer output stage consists of 2 similar blocks, upper and lower. For clarity, here we are only showing the lower block. Firstly, the sum of the lower multipliers, or all of the multipliers, is selected. Note as well that the output of the floating point multiplications can also be selected here. These are discussed later on. This result is then added to, subtracted from, or accumulated with other data sources. These sources include the local LRAM register file output. This allows for easy reuse of existing results. The cascaded output from the MLP below via the cascade input. This allows for a column of MLPs to sum all their results when configured in a wide filter function, such as a multi-tap FIR. Thirdly, the feedback output of the adder, allowing for accumulation of multiple values. The result of the adder accumulator can then be routed to the MLP outputs. Note that as well as the direct output, there are also a number of supplemental outputs which can go direct to the register file as well as cascaded outputs to the MLP above. Finally, remember there are two parallel integer output stages. These can either be combined or output in parallel. In addition to the 16 integer multipliers, the MLP also contains two 24-bit floating point multipliers. These can support floating point numbers of either 16 or 24 bits, with either 5 or 8-bit exponents. The output of the two multipliers is also summed. This allows for either each multiplier's individual result or the summed result of both multipliers to be passed to the next stage. The floating point output stage shares much of its circuitry with the integer output stage. Similarly, it can also be considered in two halves, upper and lower. Within the lower half, the selection is made between the output of the lower multiplier or the sum of both multipliers. The results are then added or accumulated, the same as in the integer stage. To aid with usage of the MLP, Achronix has created a number of library components. They leverage the full power of the MLP, but with much of the detailed settings pre-configured. This allows these components to have simplified interfaces and so are easy to instantiate and set up in a user's code. The integer library consists of the following: int mult to multiply two integers, int mult n to multiply n pairs of integers in parallel. Up to 8 pairs can be multiplied, and the result of all 8 multiplications is available at the output. Int mult add, which multiplies n pairs of integers and sums the result. Up to 16 pairs of integers can be multiplied in parallel, and the result is the sum of all the multiplications. In addition, there's a floating point library, which, as can be seen, supports a wide variety of functions. This includes complex vector multiplication within a single MLP. All of the library components also have optional accumulation, making them ideal for assembling filters or convolutions where a number of data points need to be processed and the cumulative result calculated. I hope this video has helped you understand the powerful features available in the MLP. If you wish to understand this part in further depth, or any of the other elements available in the new Achronix 7nm family, then please access the resources on screen. To see our other videos or to contact us for full documentation, please visit the website. If you have any further questions, please contact us at support@achronix.com. Thank you again for choosing Achronix.